Hello, welcome to an OpenStax video lecture in astronomy. Today we'll be covering Chapter 1, and we'll look at a brief tour of the universe as we know it today, and we'll try to cover some vocabulary along the way as well. So astronomy, what is astronomy? Well, it's really the study of trying to understand objects that lie beyond the Earth. And a bit hesitant on that definition because really astronomy is a jack of all trades. We'll be putting on our physics hat, and to understand laws of physics in the universe, we really have to understand how they behave here on Earth. We also put on our geology hat, and we have to explore the Earth before we talk about or infer ideas on other planets. Our mathematician hat will be played. We also put on a chemistry hat. And if we want to study exobiology, so studying life outside of our planet, we even have to focus on biology. So astronomy, really a jack of all trades, but our goal is to understand objects that lie beyond the Earth. And currently today, we have the luxury of studying astronomy out of curiosity, right? What is our broader meaning? What is our place in the cosmos? Now, in any science class, we focus on hypotheses. So what that is just an educated guess. We use our scientific method, which really just observes. We kind of gather information, we make predictions, and then we modify that. It's kind of an ongoing cycle. And what that is just an educated guess. We never say it's set in stone. We're always able to modify it. And as we learn more or gather more information, we want to update our hypothesis or our educated guess. And so that's the scientific method, and the scientific theory is really a model that explains that. In science, we also focus on the axioms, and there are two. One is there is no absolute truth, and the second being all things being equal, that the simpler explanation is better. These two, along with one more, will make up the hallmarks of science. So again, there is no absolute truth. So everything we know now, we are subject for it to be changed. As we learn more information, it's possible that our understanding will change. And so we have to allow for that, for things to be modified. Occam's razor of simplicity, again, if there's two rivaling models, if one is a lot simpler of explaining things, we'll typically use that. So we never want to overcomplicate things or introduce a new idea that challenges new values or ideas that we have. So if it does not offer a better explanation. And also for the hallmark, the third component making these the hallmarks is that scientific model cannot include divine intervention. So when we make these educated guesses and explanations, we're not going to rely on some magical force, something outside of us. Will typically stay away also from faith as explanations. We want to make sure things are observed. And this is not to say that the scientific model is better than any other explanation. We'll look at in Chapter 3 how that came to be. And all we are following is a current model that was set up during the rise of our current modern science model. So let's cover some vocabulary and definitions of some objects we might encounter in this class. But as we do so, we'll try to put a size or value to these objects as well. So let's talk a little about the metric system. And so a meter is equivalent to probably about one large step. So as you walk into your next class, take one large step, maybe take two, take three, so you could kind of get a sense of what a meter will be like. But one large step is typically what roughly about what a meter will be. And so we're used to our current English system with miles. And so how does that actually convert? Well, our conversion factor is going to be about 1.5. And so the easiest way to do that is the Earth is about 8,000 miles across. And so let's go ahead and take half of that. So what is half of 8,000? And we're going to get 4,000. Now let's add that half to the original amount. So that's going to be our 1 whole, and then we're going to add half. So roughly about 12,000 kilometers. And we see that's roughly a ballpark, so technically it's about 13,000 kilometers, or 13 times 10 to the third. But just a good estimate to kind of get a sense of scale here. And so we're looking at something that's about 10 to the power of 3. So that just means you have 3 zeros following it. If we look at some other planets, and so here we look at Neptune, which is about 50 times 10 to the third. And again, planets, we're going to be saying it's about a factor of 10 to the power of 3. So about 3 zeros on that. And planets orbit a star, in our case, the sun. And that's usually what we consider a planet. A few other technicalities on there. So large enough for it to kind of form round, to be a spherical shape. And then it has to clear most of the objects on there. And so Pluto, as we'll later learn, used to be a planet, but didn't quite meet those conditions there. But 10 to the power of 3, as we're talking about planets here. What about a star? Well, that's just a huge ball of gas. So it generates a lot of heat and light. Our sun, which is a star, is about 1 million kilometers across. So that's about 1 times 10 to the 6. So about 3 more zeros. So we're talking about 1,000 times bigger now as we're comparing planets to stars. And Betelgeuse, which is a supergiant star, is about 1.6 kilometers across. So that's times 10 to the 9th. So about 1,000 times bigger than our sun. So stars are getting very, very large here. What about a moon? Here we have Ganymede, which is about 53 times 10 to the power of 2. And our moon is about 35 times 10 to the power of 2. So again, about 2 zeros there. So a bit smaller than a planet there. And this is an image of Ganymede, one of Jupiter's moons. What about an asteroid? And asteroids are just small leftover pieces of debris. And so here we see the kind of potato shape, but very small, about 33 kilometers across, 940 kilometers across. So very, very small objects, relatively speaking, to planets and stars. Comet, roughly about the same size here. We have the nucleus, which is the head, about 10 kilometers across. And again, they're just leftover debris, but these are typically found on the outer part of the solar system. Which means they are ice-based frozen, very cold out there. And so that nucleus, very, very small, but if we look at the actual tail there, this factor scales about 10 kilometers, and so we could actually see that out there. So the tail, extremely, extremely large, about 50,000 million kilometers, right? As opposed to just the size of the nucleus there. So it's that huge tail of dust that makes that usually gives it size. What about a solar system or a star system? And so we're talking about our solar system is about 285 times 10 to the 9th. So extremely large here. Now again, Betelgeuse was about 1.6. Now we're talking about 285. So significantly larger here. And what about a galaxy? Well, galaxies that we're talking about, star systems, contain about millions to trillions of stars, Our Milky Way galaxy, we believe, contains about 100 billion stars or so. So how wide is that? 9.5 times 10 to the 17th. So we're talking about 17 zeros following that number. And the universe. The universe is the sum total of all matter and energy combined. And we'll talk later about the size of this. Measuring this in kilometers is just extremely a small unit in comparison to the size of it. The universe is extremely large, so we'll have to come up with better units. So one of these units is an astronomical unit. This is the average distance that the Earth is to the Sun. And it's not a set distance. We orbit around in an elliptical orbit, and in perihelion, we're slightly closer than in aphelion. So 147,000, or 147, million kilometers at 152 million kilometers. That distance, that difference is very small. The orbit is almost a circle. I believe the eccentricity is about 0.02. So very close to a circle being 0. But nonetheless, still elliptical, and it's roughly about 93 million miles, the distance. We could also introduce a new unit called a light year. And a light year is the distance that light travels in 1 year. So light travels at about 186,000 miles per second. That's extremely fast, or about 300,000 kilometers a second. So very fast. Traveling, at that speed for a whole year, 24 hours a day, 60 minutes, 60 seconds, converting that factor, we're going to get a number that's about 6 trillion miles or 10 trillion kilometers. So extremely large distance, and we call this a light year. What are some of the consequences of light travels? Well, let's first explore how far we would actually be traveling. So in about 1 second, traveling at 187,000 miles per second, we would be pretty close to the moon. The moon's about 250,000 miles away, but imagine that in 1 second, you would be out to the moon. Traveling at that speed, it would still take you about 8 minutes and 20 seconds just to get to the sun. And imagine traveling that far for a whole hour, for a whole day, a week, a month. Traveling at that speed, you would have to travel 4 years and about 3 months or so just to get to the nearest star system, which is Alpha Centauri. It's a triple star system. And traveling at that speed, just to get to the nearest galaxy, it would take about 2.5 million years. So you can start getting a sense of the scale of how far away objects are from one another. And so the light year becomes a better unit of measure rather than kilometers. So we've heard some things about, traveling at the speed of time, a speed of light, and time travel, maybe in some science fiction. And so what happens is that it takes time for light to actually travel, even though it's very far. So when we look at objects that are very distant, we're not getting those photons from today. We're getting those photons, those light beams that left, millions of years ago. So when that light actually hits us, we're seeing how an object looked when that light left. So in a sense, looking through a telescope is like looking back in time. We're able to see objects as they were. So if we wanted to look at our closest neighboring galaxy, the Andromeda galaxy, when we look at that light, it's 2.5 million years old. It left that long ago. So we see that galaxy as it was 2.5 million years ago. If we want to see how that galaxy looks like today, we will have to wait another 2.5 million years for that light to actually reach our eye. And this leads us to what we consider the observable universe. And observable because there could be something beyond there, but the light hasn't traveled far enough to reach us. So we haven't received that light yet, so we can't actually see there. So not to get confused, time we measure in years, and light years is a measure of distance. So the universe is about 14 billion years old, and the distance right across there is going to be about 14 billion light years. So not to get those two confused there, time and distance. And so the age of the universe, 14 billion years old. How large is the universe, or the observable universe? We see about 14 billion light years. And so let's take a quick tour of the universe, covering a few more objects, or pinpointing where exactly our place is in the cosmos here, kind of our cosmic address. So we live in a planet, and this planet orbits around a star, or the sun. So that's called a star system. And then there are millions, billions, even trillions of stars inside a galaxy. Our galaxy, as we said, holds about 100 billion stars. Then those galaxies cluster up together, what make clusters, and then they make these groups. So our local group contains about 40 galaxies. And those cluster up together and make what we call superclusters. And there are these large chains with empty voids between them. And even objects bigger than that, now we believe that there are perhaps walls also made up of superclusters. And then all of that together is what we call the universe. And it contains billions of galaxies, each containing billions of stars. And this begs the question, well, the universe has so many stars. Are there an infinite number, or is there a set number? And so if the universe had infinite stars, that means whenever you look out in a direction, we would see a star, and we would get a little bit of white that blocks out that portion of the sky. Well, if this happened everywhere, eventually any direction you looked, you would have light coming at you. And the night sky would not appear black, but rather it would appear white. So the fact that it does not appear white tells us that there's not an infinite amount of stars, but that means that there should be a finite. But what exactly is that number? And so next time you go to the beach, pick up a pinch of sand, put it inside your palm, and see if you could count the grains of sand inside of there. So 100 billion stars per galaxy, and there's 100 billion galaxies. That's 10 to the 11th times 10 to the 11th. That's 10 to the 22nd. That's a 1 followed by 22 zeros. That's a huge number, astronomical. It's almost incomprehensible how large that number is. So think about that daunting task to count all the grains of sand just in your palm. Well, imagine counting all the grains of sand on an entire beach. Well, 10 to the 22nd is all the grains of sand on all the beaches in the entire world. That's what 10 to the 22nd is.